Okay, folks, and hello out there. We're on the air. It's uniform distributions tonight. So today we're going to look at uniform distributions. This lesson isn't as intense as the other ones. I mean, the first one was kind of intense because we talked about a lot of new things. There's only a couple new things that we're going to talk about here. So let's go ahead on to it. So a TV game show. On this one, Allie has the option of taking home either $750 or choosing from one of the 26 briefcases that contains $1 million. What of her chances are winning? Well, if we look at probabilities again, so the probability of winning is the total number of winning cases over the total number of cases. So how many winning cases are there? Well, there's 1 and there are 26. So the probability of a win is 1 in 26. Is each briefcase equally likely to hold the money? So yes, each briefcase it's in one of these 26, so they're equally likely. So then what option would you do? I mean, nowadays it's a little bit different because $750 isn't like huge amounts of money, right? Like if someone was like, oh, I could have won $750, you know, it's like, oh, that's only a couple of paychecks. However, the chance of like a 1 in 26 chance in like a 5%, 4% chance-ish, a little bit less than 4, of getting $1 million is probably a risk that most people are willing to take. And then how would this change if she were allowed to a second chance after checking the contents of 5 briefcases? Well, if she looks at the contents of 5 briefcases, clearly if one of those is the winner, well then that would be easy. She would just pick that one. But if she looks at 5 and they're not the winner, well, that's going to reduce our total from 26. We reduce it to 5. It'll be 21. So now it's going to be 1 out of those 21. So the probability of winning will be 1 out of 21. So definitely awesome if you could have that sort of option. So you basically have a 1 in 5 chance now, or a 5% chance. So not a 1 in 5, 5% chance of winning $1 million. So we're going to look at some uniform distributions. So I want you to create the probability distribution. So don't forget the probability distribution is just we have our values and then we have what the probability of each of those will be. And then we would graph those and that's what a histogram would be. So we just want to create the table first of the probabilities of the upper face on a single roll of a die. Okay, so let's just look at single roll of the die. So what are my X values that I can get for a single roll of the die? Well, I have 1, 2, 3, 4, 5, and 6. And what's the probability of those? Oh, my things are so crooked. What's the probability of those? Well, the probability of 1 is a 6, 2 is a 6, 3 is a 6th, and it continues down. They all have 1/6. Okay, so that's A. B, I had to deal with this spinner. So looking at this spinner over here. So it has 8 pieces total, but what are the values that you could potentially get? So you've got a 1, 2, 3, 4, and 5. So what's the probability of getting a 1? Well, let's look. 1 appears 3 times. So it has a probability of 3/8. The 2 appears twice, so it's a 2/8. The 3 appears once, 4 appears once, and 5 appears once. So these are all 1/8. We're going to skip the last one just so I can save time. Sketch a probability. So sketch the histogram for each of these. So if I were going to, I'm just going to do a rough sketch of them here. And again, if I have 1, 2, 3, 4, 5, and 6. Well, 1 had a probability of an 1/8. So I'm just going to use 1/8 is my scale. 1 had a probability of an eighth, 2 was an eighth, 3 was an eighth, 4 was an eighth, 5 was an eighth. So it's just a solid block. Oh, gosh. Okay, solid block, all the same height. Okay, let's look at this next one. 1, 2, 3, 4, 5. And what I'm going to do is, again, I'm going to go up by eighths. 2, 3, up to 3/8. Oops. And we've got 1, 2, 3, 4, and 5. Well, 1/8, 1 had a probability of 3/8. 2 had a probability of 2/8, and the rest was just 1/8. So what they want you to do is compare the three. We'll compare the two distributions. How are they similar? How are they different? Well, notice in this one we've got one constant value all along. Here we have, oh, where'd my cursor go? Oh, there we go. Two different values, and then it's this constant piece. So that's the thing that they have similar, is that one constant value. Yes, they're both at 1/8. No, this shouldn't be an eighth. This should be a sixth. Both a constant value over a couple values of x. How are they different? Again, this one has two changing variables at the beginning. So, moral of the story, blah, 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 blah. This is known as a uniform distribution. So why is it uniform? Well, uniform means all the same. If you look at the probabilities, it all has the same probability. So things like rolling a die, flipping a coin, anything that's the same probability of outcome. If you have a spinner, actually, so here, how could I make the question with the spinner such that it is a uniform distribution? Well, to make it a uniform distribution, I would have to have it so that these ones didn't have these extra ones. So they all had the same equal chance. So if there were 5 spinners, like 5 colors, or 5 numbers, each one would have to have an equal value so that there would only be 5 pieces on it. So going back up here, going back up, pull this out. Oh, not that. Pull this out. There you go. A uniform distribution occurs when, in a single trial, all outcomes are equally likely. So, for all outcomes x, p at x is equal to 1 over n, where n is the total number of outcomes. If you're looking at drawing hearts out of a deck, right? So there are 13 hearts out of the total. So you're going to have a 1 in 4 chance of grabbing a heart. Again, just if you take it out and put it back in. Just things like that. So whenever the outcome is the same, you have the same number of opportunities for each. Same idea if we had, a bag with 5 different colors and like five marbles, each one is a different color. So each one has an equally likely chance to be drawn as long as it's then put back into the bag. Okay, so today we're just going to look at some uniform distribution stuff. And we're going to do some probability distributions as well as expected values. So you don't actually need the Chromebook today, but it will come in handy. You can do it on a Chromebook, that's fine, and it's pretty simple then to do on a Chromebook, but you can do it with pen and paper and a calculator. So, a calculator has been programmed to generate a random number between 1 and 5. Classify this distribution. Well, since it's a random number between 1 and 5, that means this is going to be uniform. Every number has an equal likely chance of getting drawn. Calculate the probability distribution. Well, if we have the values, oh, come on, 1 through 5, and our probabilities will just be 1 and 5 for all of them. So what will our sketch of our probability distribution be? Well, we're going to have 1, 2, 3, 4, and 5, and it's uniform at 1/5. So that means just have a big old brick at 1/5. I don't know why it's writing on a diagonal so badly. Try switching myself around. Alright, so now we need to calculate the expected value. So how do we do expected values again? Well, remember, expected values is equal to the sum of xi p at xi from 1 to n. So we need to find x times its probability for all of our terms here. Oh, excuse me. Excuse me. I tried to cover the mic there, so hopefully it wasn't too loud. So we're going to have from 1 all the way to 5. So the probability of, so we're going to fill this in. We've got 1 times 1/5 plus 2 times 1/5 plus 3 times 1/5 So we're going to add all these up. Now, notice that each of them is divided by or multiplied by 1/5. So we can either factor that 1/5 out, add all the numbers up. So if I factor the 1/5 out, we're left with 1 plus 2 plus 3 plus 4 plus 5. And that will give us, so 9, 10, 15 over 5. So our expected value will be 3. Okay, so I know it kind of went quick, but there's not a whole lot to this one. We had a uniform distribution. Our probabilities are all going to be the same because it's uniform. We have the values 1 through 5 as our options, all 1/5, and we do the sum of x p at x. So again, if you were doing this in your spreadsheet, you would just have, this would be your x p at x column, and you would say this is equal to cell, whatever this cell number is, multiplied by this cell. And then you would copy that down. Then at the bottom you would do the sum of the values above. And now that I've drawn all over my table, or chart, sorry, move it over. Okay, so you can use your you can use sheets to do that, or you can just use it on a calculator or by just pencil and paper. So again, they have all these values, same idea. They actually went forward and did the xp at x inside of the, when they calculated their probability distribution, but that you don't have to because you don't graph that. They just did that for their expectation values later on. So they just showed you two different ways of doing the exact same thing. You could have added all the tops up and then divided it by 5, or that you factor the 1/5 out and then add all the numbers up. So there's absolutely no difference there. Okay, so your turn. So go ahead, pause the video, give it a shot, and then come back to it later. This one is a little bit easier if you have a spreadsheet, so it's just less calculations. Okay. Any case, a screensaver has been programmed to draw a circle with a randomly chosen radius integer between 1 and 8. Since it's randomly generated, again, between 1 and 8, this will be uniform. Is the probability distribution of areas uniform? Yes, the probabilities of the areas will be uniform because it's looking at the radius. Is it the radius? Radius is going to be an integer value, so then you just 3 pi times r squared of area uniform. Yep. So then calculate your probability distributions. Well, your x is going to go between 1 and 8. Come on. 1 and 8, and then we have the probabilities of those is just 1/8. Okay, so then again, your graph will be uniform at 1/8. The value is 1 through 8, and it's a big old block. Yeah, yada yada yada. Sketch the graph, comment on the shape. It's just a solid block because it has the same values. So now you're going to do your expectations. So again, on the spreadsheet, you could have another column, xp at x, and you're just multiplying these. So 1 times 1/8, 2 times 1/8, da 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 da, to 8th times 1/8. And at the bottom, you're just going to do the sum. Hey, if you're doing it by pen and paper, I'll write them out here. So the expected value is equal to the sum of x p at x. And again, if you had just this part, 1 to 8, that would be fine. You wouldn't have to expand it all out, saying like it's x1 times p at x1, blah, 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 blah. We can just put the values in at that point. So we've got 1 times 1/8 plus 2 times 1/8 plus 3 times 1/8, 4 1/8, 5 times 1/8, 6 times, I don't know why I'm getting bigger, 7 times 1/8, and 8 times 1/8. Okay, so we're going to add these up. I'm going to factor the 8th out, and I'm just adding up the numbers 1 through 8. 5, 6, 7, plus 8. Just as a bit of a side note, oops, if you're adding up numbers 1 through n, a short form is taking n times n plus 1 and dividing it by 2. Does that make sense? The first 10 digits, 10 times 11. Okay, let's lose the first 6 digits. Well, let's just try with 8. Adding these all up, I'm going to get 8 and 7 is 15, 20, 36. Oh, 35. 8 and 7 is 15, 20, 30, no, 36. So we're going to have 36 over 8. And if we try this method, we would get 8 times 9 divided by 2. We're going to get 4 times 9, which is 36. So I just did 8 divided by 2 is 4 to give me 36. So I can do 8 times 9 is 72 divided by 2 is 36. So it works out the same. So if I'm adding numbers 1 through 9, I can use the short form of n times n plus 1 over 2, where n is the highest value. So then we get 36 over 8, which is 4 1/4. No, 4 1/2. So it'd be 32 and 4 over 8. So we're going to get 4.5. So therefore our expected value is 4 1/2. Okay, now we're going to talk about a couple things called fair games. So we've talked about fair games before, that kind of things have to be balanced. So let's go ahead this question and read it over, and we'll try and talk about what that means. So a game involves rolling a die. A player who rolls an even number receives the points equal to 2 times that face value. And if the player rolls an odd number, they lose 3 times the face value. Is this a fair game? So let's just look at the values of x And should I write points? I'll write points. All right, so if I roll a 1, how many points do I get? Well, you get -3. What if I roll a 2? Well, I'll get +4. If I roll a 3, I'm going to get -9. If I roll a 4, I will get +8. A 5 will yield a -15, and 6 would give us +12. Okay, so now we want to look at the probabilities of these guys. Well, it's the probability of getting a 1. Again, it's just a sixth. These are all going to be 1/6 because it's a uniform distribution. Okay, now when we're looking at our expectations, so our expected value, let's see, because why would we want to calculate an expected value? So we want to see if this was a fair game, what would be true about that expected value? Well, you would expect, if it was only fair, that the expectation would be that you would get similar to how we talked about with that ticket question yesterday, buying the tickets. If you had it equaling 0, then you had a ticket that you would break even on. So in order to have a fair game, we have to look at having an expectation, or an expected value, equaling 0. Okay, so let's find our expected values, or more appropriately if we called it xp at x. Now, since we're more interested in the points, right? So we're looking at the points, so we have to consider our points as the x, not the actual dice. Okay, so xp at x will yield a -3/6, a 4/6, and -9/6. 8/6, -15/6, and 12/6. So now the expectation again is just the sum of these. So we have to just add all these up. So I'm just going to add all the numbers again. So I have -3 plus 4, give me +1. -9 plus 8 gives me a -1. So I'm at 0. Then I'm at -15 plus 12 to give me -3. So the sum will equal -3/6, which is equal to -1/2, which is equal to -0.5. So my expected value, damn it, I did it again. Expected value turns out to be -0.5. So is this a fair game? The boys in the back are saying, yep, 100%. But no, not a fair game. If it was going to be a fair game, this would have to be 0. And that's what they did. So, your turn. A spinner has 8 equally spaces labeled 1 through 8 in a particular game. The player wins points equal to double the sector's face if a power of 2 is spun. So basically, if it's even. All others, the player loses the value of the spin. Okay. So if it's even, you double. If it's not that, so if the sector's face value is if a power of 2 is spun, so yes, it has to be, this means even, and if the other one, if it's odd, then it's just equal to the value. Okay, so again, writing up our table of what those mean. So we have 1, 2, 3, 4, 5, 6, 7, and 8. Well, if I roll a 1, I am going to have -1. If I roll a 2, and double the sector's face value, so I will get double this, which will be 4. I will have, in this case, a -3. I will have 8. I will have -5. I will have 12. Here I'll have -7, and here I will have 16. Alrighty, so that's point. So now let's look at the probabilities. The probabilities are all equal at 1/8. And now we want to find the expected value. Sorry, excuse me. We want to find x, p at x, and again, since we're interested in the points, we're using points and p at x for expected value, because it's expected value of the points, not the spins. So we're going to have -1/8. We are going to have 4/8. We are going to have -3/8. We are going to have 8/8. -5/8, 12/8, -7/8, and 16/8. Now we are trying to find the expected value, so that's just the sum of all of these guys. So adding these all up, -1 plus 4 is +3, -3 is 0. We get 8 minus 5, which gives us +3, plus 12, +15, minus 7, which is +8, and plus 16 gives us +24. So we get +24/8, which gives us a value of +3. So is this expected value, is this a fair game? Again, we've got no, not a fair game. So in this case, since we have a positive expected value, though, who would this benefit if this was like a game at a casino? Would it benefit the house, quote unquote, or would it benefit the player? So since it's positive, this would be benefiting the player. Very good benefits, actually. So they wouldn't have this as a game in the casino or as any game, because they're losing money a lot. For the previous question, if we had an expected value of -0.5, who is this benefiting? Is this benefiting the player or the house? So in this case, this is going to benefit the house. And again, only by a little margin. Like obviously by 3, you're getting a lot more out of than just a -1/2. So this could be a potential game that that you could do, and then the house would always win a little bit more than the player. Okay, so some of the key concepts: if it's a uniform distribution, then you're going to have all occurrences will have the same likely outcome. Okay, so like rolling a dice, flipping a coin. If you have a spinner that has an equal amount of things on it, it's like that. That uniform distribution, the probability is just 1/n, where n is the number of outcomes or number of pieces or whatever it is. When calculating the expectations of a uniform distribution, you factor the 1/n out, and then it's just the sum of xi. So remember the sum of this xi, so this is just, remember I always said, okay, let's just look at adding the numbers on top, and then we'll take, you factored out that 1 over where the value was. If you're adding numbers from 1 to n, it's just equal to n times n plus 1 over 2. Okay. fair game, the expected outcome of a fair game is 0. Alright? Now, for your homework, there is a sheet. It is online. There are 3 questions. Do the 3 questions. Some of them require, you can do them all online if you want, so just opening them all in Google Sheets is fine. Even one sheet, and you can just open up new tabs. And then submit. There'll be a Dropbox. So when you're done, they go into the Dropbox. This is a kind of a fairly quick lesson, so it shouldn't take too long. Alright, so with that, I am signing out. I want to wish everyone a happy Easter, and I hope they enjoy their break. See you when you get back. Craft Chick out.